So earlier in the course, we talked about finding solutions to computational problems by nibbling away at the edges of the problem, taking a problem of a larger size and creating a slightly smaller problem, solving the smaller problem, and then coming back to solving our original problem. We're going to follow that same idea that we used, for example, in the Towers of Hanoi and in insertion sort, but we're going to now train our sights on a large class of very important problems, which are generally known as optimization problems. So what is an optimization problem? An optimization problem involves choosing a solution out of many possible solutions. There's something called an objective function that assigns a value to each possible or feasible solution. So imagine, for example, that you want to drive from Philadelphia to New York. There are many possible ways that you might get there. There are many possible roads. And each road has a time to traverse that road depending on traffic conditions and so on. And so those are all the possible solutions to your problem, all the possible ways of getting to New York from Philadelphia by roads. And the objective function might assign to each path you choose the time it would take to drive on that path. And so the problem is you have a set of possible solutions, and you have an objective function that assigns a value to each possible solution. The optimization problem then is to find that solution which has the maximum value in some cases or the minimum value in some cases. Those are the keywords, maximum and minimum, that make it into an optimization problem. Of course, in the case of driving, you would probably want to find the solution that has the minimum value. But if you're collecting rewards, then you might want to find a solution that has maximum value. Optimization problems are absolutely everywhere. Let me give you just a few examples. I'm sure you can think of some yourself. So one thing that we just talked about is finding the shortest path from point A to point B, given the time or distance along various segments of the path. Another problem that might be very important to you is that you have a monthly budget for your expenses. You can buy various things within your budget. Now, each thing you buy has a certain value for you. Food might have a certain value, clothing might have a certain value, and within food, different items might have different values. Now, how do you maximize the total value you get for all the things you buy, but stay within your budget? That is an optimization problem. And that's a very important problem that we solve every month. Another problem that comes up more in biology, and we will see this more in detail, is suppose you want to transform one string into another by editing the first string repeatedly. What's the fewest number of edit operations you need to make to transform one string into another? And we will see why this problem is important in a bit, but this is an important problem. One more example, two more examples actually. One more example is suppose you want to build a new town or a new city, and you want to locate K hospitals in the city. But you want to locate them in such a way that every resident of that city can get to a hospital nearby without too much travel time. How do you minimize the travel time for every resident while locating K hospitals in a city? That's an optimization problem. Another problem, you sometimes want to compute a function using an algorithm. This is a little bit self-referential, but how do you compute the function in the fewest number of steps, a minimum number of steps? Again, an optimization problem. So I hope you're convinced from these examples that optimization problems just have to be solved all the time. And we will see some techniques for solving optimization problems that do this idea of taking a bigger problem, nibbling at the edges of the problem, and reducing it to solving a smaller problem. Of course, if you have an optimization problem like finding the path from Philadelphia to New York, let's say, one thing is to look at all possible ways of getting from Philadelphia to New York, all possible paths from Philadelphia to New York, taking the objective function value for each one, and then taking the minimum. This is usually called the brute force approach, where you absolutely examine every possible solution and find out its value and then take the best solution. Unfortunately, this brute force approach can be very, very slow because typically there are exponentially many paths to get from point A to point B. And in general, for any optimization problem, there are exponentially many solutions. So you really don't want to do this brute force approach. You want us to do something cleverer that implicitly examines all solutions, but still runs very fast. And in the next few segments, we're going to look at a very important algorithmic paradigm called dynamic programming. It's a way of finding the optimum solution to certain optimization problems, not all of them, but a good number of them. And it's very efficient when it works. So what we're going to see is, what is dynamic programming? How can we use dynamic programming, and when can we use it? Those are the questions that we will be answering in the next few segments.